Okay, so welcome to today's TH colloquium. So this talk kind of doubles as the usual colloquium of the theory group at CERN. And at the same time, it's part of this ultra-high frequency gravitational wave workshop that we've had this week. So during the workshop, we're discussing various ideas, various concepts of looking for gravitational waves at very high frequencies. So that means beyond the frequency range of LIGO, so a range which is interesting for the search of new physics, for exploring the universe. There's plenty of room in the front, so don't be shy to come to the front, and also don't be shy to move in a bit, so you leave a bit room on the sides for people to still come in. So as such, this workshop brings together both theorists and experimentalists. So we have a very mixed audience, and we have a lot of very, very exciting discussions. And the workshop will be going on until tomorrow afternoon, and of course everybody is very welcome to join. Now I need to keep talking until everybody is here and settled. So I say again, there's plenty of room in the front. And do move into the middle to let people join on the sides. It's the usual phenomena that colloquium 2 o'clock means that's when you leave your office, right? And then, okay. So with this, it's a pleasure to announce the speaker of today, Gabriele Franciolini. So Gabriele just started as a postdoc here at CERN. We're very excited to have him at CERN, and we're excited to have him here for this talk today. He's an expert on everything related to primordial black holes in the universe. And the floor is all yours.
Thank you. So is the mic working? Do you hear me? Okay. Thanks, Valerie, for the introduction, and again, thanks for having me to give this colloquium today, and for inviting me to talk about primordial black holes at this nice workshop. So the topic of the workshop is searching for new physics in the ultra high frequency gravitational wave window. But I wanted to start by setting the stage. So when we talk about the spectrum of gravitational waves, the image that we have in mind is usually this one. So this is a nice image by the European Space Agency. So I'm collecting the main experiments that we know are trying to observe gravitational waves in terms of the time scale of the gravitational wave, or if you want, the inverse of the frequency. So on the very right, you see CMB is a very good probe of gravitational waves that have a period that goes up to billions of years. So we are talking about gravitational waves of cosmological scales. Then, at smaller periods, we have pulsar timing arrays that can search for gravitational waves with a period that goes close to years. And these are really galactic scale gravitational waves. And in astrophysics, we know mergers of supermassive black holes can produce this kind of gravitational waves. And there's also some excitement on this following the recent data release by various collaborations. Then there is a planned experiment in the space, so it's an interferometer looking for gravitational waves with a frequency of around the milliyears, and this is called LISA. It's going to be launched probably in the next decade. And then we all know about the LIGO Virgo Cagra experiments that are searching for gravitational waves in the range of frequencies of around 10 to kilohertz. So in this window, we all know astrophysical objects like stars and black holes can produce gravitational waves, and these have been observed. And there are ongoing searches for these kind of objects. And in all this window, we know cosmic fluctuations in the universe can produce signatures or very different phenomena in the very early phases of the universe. Now, where is the ultra-high frequency window? We need to move it a little bit on the right, and you see that we are talking about timescales that goes much below what LIGO is observing and frequencies beyond the kilohertz. And here, there are only a certain category of sources that could show up. And we could try to categorize them in two ways. So one is a cosmological background. So to understand the scales that are involved, typical sources producing gravitational waves in the early universe are related, have an emission process that relates the frequency to the Hubble scale at the time of formation. And this Hubble scale is, of course, related to the temperature of the universe at that epoch. So following this relation, you see that searching for gravitational waves beyond the kilohertz in this ultra-high frequency window would correspond to searching for events that took place in the early universe at very high temperature. But then you can also search for collisions or mergers of compact objects that, however, have different properties than the one that LIGO has already observed. And the typical scale for this collision, or if you want this kind of mergers, is given by the ISCO frequency or distance. This is the location of the innermost stable circular orbit. Beyond that point, the binary basically plunge and produce a new object, most likely another black hole. And this scale is associated to a maximum frequency of your signal. And this is the ISCO frequency. And if you look at this relation, you see going beyond the kilohertz necessarily is associated to mergers with masses that are below the solar mass. So we are looking at if those are black holes, for example, these are below the Chandrasekhar limit. And we know in astrophysics you don't expect to form them. So this relates quite nicely with the main topic of the talk, which is primordial black hole, in fact. These kind of objects are not bounded by the Chandrasekhar limit just because they don't form out of stellar evolution, but they could be formed in the early universe from the collapse of very large overdensities. So in this picture here, you see the entire evolution of the universe. You see structure formation on the right, the standard lambda CDM model. But we don't know what happened in the early stages of the universe. It could be that there were density fluctuations that were so large to produce population of objects of this sort. And the mass of this object, as I said, is not bounded by the Chandrasekhar limit. It could be quite below the solar mass. So this was kind of to set the stage, and this is the actual outline of the talk. So we'll start with an introduction to the physics of primordial black holes, and then I will spend some time discussing the properties of the binary that are formed in these scenarios, and what are the rates for these binaries to merge. So this is the fundamental question we need to answer to understand whether or not we expect to have mergers sufficiently close that we could see them with the sensitivity or your preferred detector. And then I will plot this line in the ultra-high frequency window to see how many orders of magnitude we need to catch up to then hope to discover a population of these kind of objects. So let me start with the introduction. The idea that you could form these kind of objects dates the 60s. Actually, the first paper on this was by Zeldovich and Novikov, and this was kind of setting a constraint on PBH already. So the idea is that if you had objects that were within the Schwarzschild or scale, so they would be basically black holes in an expanding universe, the issue they wanted to address is whether or not they could accrete so fast that their mass will scale with the horizon. So what they thought is that an object produced in the early universe with such properties would then be incompatible with cosmology, because we would end up with cosmological size black holes. But then this was later on proven that this doesn't happen by Carr a few years later. And also then Hawking kind of went in a similar direction, so he kind of thought about possible production mechanism for these objects. So he wrote in his abstract, if you have sufficiently large fluctuation in the early universe, you could produce black holes. And he also suggested that you could search for this population of objects because they could be captured by stars. So this is something that 50 years later is still debated and could lead to some constraints. And then Carr, that was a student of Hawking at the time, further developed the field together with Hawking and compute for the first time the mass distribution depending on the statistics of perturbations in the early universe. And also, I think it's nice to mention that Hawking apparently by it was narrated by Carr that he ended up thinking about the Hawking evaporation, thinking of small black holes that could be produced in the early universe. So this was kind of followed up by after the first paper on this topic. So this, I think, is quite nice. And then the connection with cosmology was later on done by Chaplin. That he was the first to suggest that, of course, primordial black holes will be contributing to the matter in the universe, and now we know that they're contributing to the dark matter. They could be contributing to the dark matter. And of course, the field has developed a lot since those days. Now, of course, this was kind of a roller coaster. As you can see, this is just to give you an idea of the number of papers on the topic, dating since before the early 2000s. And there were moments of excitement, and then later on, like with new constraints on the scenario, people started thinking about something else. But as you can see, there is a pivotal moment around 2015 when really the attention of the community was brought on this topic. And this is, of course, related to the discovery of mergers of black holes by LIGO and Virgo, and the appearance of this paper in particular, but also other groups suggested similar things, that potentially these objects could be related to the dark matter. And in particular, they were talking about, of course, primordial black holes of around 30 solar masses. Now we know that indeed in this mass range it's not easy. So far it's quite constrained, the scenario for these kind of masses to explain all the dark matter, but it is not ruled out in other mass ranges, and we will see. And then also there were other kind of observations that also could be related to primordial black holes, but we don't know. So the main message that I want to convey is that gravitational waves are for sure an interesting new way to probe this population of objects. And the excitement is due to the fact that we can constrain these scenarios quite well. And in a decade or so, we will set very strong bounds, and we will know whether or not primordial black holes has to do with a dominant component of the dark matter. Now, the idea when you consider scenarios that are forming primordial black holes is quite simple, if you want. So you have a field of density perturbations in the early universe. So if the density perturbation is so large that it overcomes a threshold, it can collapse to form a black hole. Now, this threshold is by now understood to be around order 0.5, and there are different groups producing numerical relativity simulations that are able to describe the phenomenon and in particular give us the details of the threshold that could allow for the formation of black holes in the early universe. And if you want to understand what is the mass of the black holes and how is related to how that is related to the density perturbation that produce the collapse, the idea is the following: you have these density perturbations that are on scales, on super Hubble scales, And we know in the early universe, at least in the standard scenario, you have a phase of radiation domination. The Hubble scale grows compared to the physical scales. And when this overdensity re-enter the Hubble radius, it can collapse if it's sufficiently large. And the mass that ends up in the black hole is related to the mass contained in the cosmological horizon. So as you can imagine, as the horizon potentially can span a huge range of values, the mass of the black hole could fall in a much greater range compared to what you have in astrophysical scenarios. And then the whole point is that this population of black hole on sufficiently large scales behave as a component to the dark matter, and constraints on this population are usually set in terms of this fraction, so the abundance in the primordial black hole sector compared to the abundance, the measured abundance of the dark matter. So FPBH equal to 1 will mean that in your model all the dark matter is in this type of objects. And this parameter is important also for what we'll be discussing because it's control basically the number density of these objects. Of course, that depends on the overall abundance and the mass in your scenario. But the formation of these objects, at least initially, must be rare, and this is almost a trivial consideration. The whole point is that in the interesting mass range, for phenomenological reasons, you can easily show that these objects form at very high redshift, much before the matter radiation equality. And then, of course, after formation, they scale as a dark matter component compared to the dominant scaling in a radiation-dominated universe. So their density compared to the radiation fluid is enhanced. And in fact, they reach equality, contributing to a given fraction of the dark matter at a redshift of around 3,400. And the point is that this enhancement means that at formation epoch, the probability of having Hubble patches collapse into black hole should be a very small number. Otherwise, you would overclose the universe. And this creates some problems in the sense that since this is a rare event, you are sensitive to the tail of distribution of your perturbations, and also, in particular, the deviations from Gaussianity and details of your PDF that describes the perturbations. Now, there are many ideas on the literature on how to produce these objects. The fundamental way is you need to have large perturbations, as I said many times already. One, maybe the most studied scenario, assume that you have really scalar perturbations that are enhanced at small scales. So you should consider this usual scenario on how you form perturbations in the universe. You may invoke inflation. You know at sufficiently large scales, these perturbations are small. The power spectrum is around 10 to the minus 9, as it is quite well measured by CMB experiments. However, we don't know what is the spectrum of this perturbation at small scales. If you can generate an enhancement of scalar perturbations, then you can reach values that will produce a significant population of primordial black holes. And this can be done by, if you want to play with models of inflation, the simplest way is to introduce some features in the evolution of the inflaton, such as an ultra-slow roll phase that will generate such enhancement, or you can invoke multi-field models or the curvaton scenario. There are many ideas, and I won't discuss them in detail here. Another very well studied way to produce primordial black holes is invoking first-order phase transition. So the idea is very simply that you have a scalar field that develops a false vacuum and transition to the true vacuum through nucleation of bubbles. So the first proposing this scenario to form primordial black holes was Hawking himself, and he thought that collisions of bubble walls could in regions of space could have so much energy that the energy density would be enough to produce the collapse. But there are other mechanisms, and in particular also recently was quite well developed the idea that if the transition is strong enough and lasts for a long time, there may be regions of the universe where the field remains for a longer time in the false vacuum, and you have sufficient energy density to induce a collapse. But there are also other mechanisms that you can find in the literature. But this is just to give you more or less an idea of the most studied scenarios. Then, of course, we should understand what is the cosmology of these objects. So if they make a very small fraction of the dark matter, they probably are very difficult to be seen. They don't modify the usual lambda CDM predictions. However, if they are a significant fraction of the dark matter, they could lead to many interesting signatures. So the time evolution of these objects goes like this. They are formed at very high redshift. They could already, some of them could pair in binaries already before the matter radiation equality. This is something that we'll discuss more in details, just out of decoupling from the Hubble flow of pairs of objects. And then in the late-time universe, you may have different phenomena that are modifications of the standard lambda CDM scenario. And some of them, just to give you an idea, is if they're small enough, they could evaporate through Hawking evaporation and emit particles that could be seen in different ways or could have effect on the CMB and so on. Then they could modify the small-scale structure, like how structure formation proceeds at small scales. And if they are sufficiently massive beyond stellar mass, the accretion onto this population of objects would also emit electromagnetic radiation that could have all sorts of impact on CMB and other kind of observations of electromagnetic radiation. And then, of course, mergers, which is exactly what I'll be talking mostly in the second half of this talk. And also, they could lead to lensing signatures. So experiment looking at distant stars could be sensitive to primordial black holes passing in a line of sight and could potentially pick up signals of this population. So the way we can search for these kind of objects, I think it was nicely put in contact with particle dark matter searches by Eli Koves some years ago. So you may be familiar with this kind of graph here. So this is kind of a summary of the strategies that you can use to search for particle dark matter candidates. So on the left-hand side, you have two dark matter particles. You have standard model on the right. So going in one direction would mean searching for evidence or either annihilation or decay of your dark matter particles. So this is the indirect detection. Going from bottom to top will just mean that your dark matter particle bumps into your detector, interact in some ways with known matter, and this goes through the name of direct detection. And also you have possibility of forming dark matter particle from standard model particle. This is the production channel, and you could search for this for example, at LHC. So one could use analogy and categorize the ways in which you can study primordial black holes, search for primordial black holes in a similar manner. So you have two black holes. So if you go on the right, this is the way of indirectly searching for them. And I mean, collision of those emits gravitational waves. So these are really, the indirect detection in this case is really looking for primordial black hole mergers through gravitational waves. Going from bottom to top, you have your PBH interacting with standard model in the sense of, in this case, astrophysical context or cosmological context. So what was mentioned already, like lensing impact on CMB through emission of electromagnetic radiation, dynamical effects on galaxies and structure. And also, it is possible to search also in the left direction, like not really producing primordial black holes, that is quite unfeasible, but testing the formation mechanism. So this is quite a violent process. You have a large perturbation, and they are typically associated to emission of gravitational waves. But in this talk, I will focus on this indirect way of searching for these objects. And this is a summary plot of the constraints on primordial black hole population. These assume you have a narrow mass distribution at the given position on the x-axis. So this is the mass. And you see it spans from 10 to the minus 18, which is, in fact, 10 to the minus 19 is the typical number for the mass that will evaporate through Hawking in a timescale comparable to the age of the universe. And then goes up to beyond the stellar mass, up to supermassive black hole values. But as you can see on the right, it is quite well constrained. So very briefly, what I want to point you at is that first the fact that there is still an open window that we want to constrain, and there are some ideas, but so far there are no robust constraints on this parameter space. So these are masses that are usually called asteroidal mass for obvious reasons. And on the left-hand side, you have constraints from the emission of particles through this Hawking evaporation. So these are objects that have not yet evaporated, but their luminosity is still sufficient to be potentially detected. Then here you have constraints from lensing searches. Then here in the stellar mass range, there are constraints by measurements of the merger rate of stellar mass black holes by LIGO-Virgo-Cagra. So this is a constraint that comes exactly from this indirect logic. And then using gravitational waves. And then tight bounds goes quite steeply down here beyond 100 or 1,000 stellar masses, because accretion around those heavy primordial black holes is emitting electromagnetic radiation in such a way that you would impact CMB and would be incompatible with Planck observations. But also, okay, as you can imagine, we want to close this window because, of course, here primordial black holes are still a viable dark matter candidate, but there are also observations, in particular in the lensing experiments, that picked up some events, and then at the moment we don't know what they are. It's very hard to argue they are primordial black holes, but still the collaborations were not able to explain those events. Auger, for example, is looking at stars in our own Milky Way and detected an event with a typical timescale for this lensing event, which is not compatible with the population of astrophysical objects we know exist in our galaxy. And so far, we don't know what it is. It could be a floating planet. It could be a primordial black hole. We don't know. And the parameter space to be compatible with this signal is here. And the Subaru experiment that is looking at light from a nearby M31 galaxy also saw a lensing event with a mass that would be falling in this around 10 to the minus 10 solar masses. So it is what I want to say here is that it is important to develop new ways to search for this parameter space, and this will help us also interpreting what's going on in some of these strange detections, let's say. And then also, of course, close this window at some point or discover something there. And so now we come really to the ultra-high frequency window, because if I plot in this panel, on the top you see the ISCO frequency associated to these masses. You see that mergers of these kind of masses will end up in the ultra-high frequency range beyond the kilohertz up to which you can probe gravitational waves with LIGO. So we will see that searching for mergers in this beyond the kilohertz could, in principle, tell us about population of objects at masses smaller than the stellar mass. Okay, so Now we need to describe how the binaries form in these models and what are the rates for these binaries to merge and produce gravitational waves. Now, the initial conditions for the distribution of primordial black holes in the universe, at least so far in most of the models, is the following. So it is characterized by a Poisson distribution. So they are randomly distributed in the universe. When I say randomly, I mean that the two-point function of their location in the universe is characterized by the Poisson noise. So they're randomly placed in given Hubble patches. And the way you can understand that they are not clustered beyond this initial random position of them in a volume is the following. The only way you would have to correlate their location beyond random would be to have a longer overdensity that would push small fluctuations beyond the threshold. However, the amplitude of these long wavelength modes in terms of density contrast, which is the quantity that ultimately could push beyond threshold, this amplitude is very small. The reason is that these small scales are re-entering the Hubble radius at the time of collapse. So the Hubble radius is around the size, the wavelength of these small perturbations. And so these long wavelengths are super Hubble scales, and they are suppressed by gradient squared of the curvature perturbation. So in practice, in generic scenarios that form primordial black holes, they are not clustered initially, so at very high redshift when you form them. There is a little bit, a small caveat about this. You may cluster them if you introduce very specific local non-Gaussianities, but this is quite specific. We will come back to that later on, but in standard scenarios, these are the initial conditions. And then, of course, this does not mean that they do not cluster following the evolution of the universe. So they are, of course, if they are a large fraction of the dark matter, their Poisson noise in their density could drive early structure formation at small scales, but this only happens for values of FPPH large close to unity. Otherwise, they just follow the lambda CDM distribution of cold dark matter. And here you see 3 snapshots of a numerical simulation performed by Inman, Elie, and Mood. So in these 3 panels, they're showing different cosmologies at redshift of around 100. Depending on the abundance of primordial black holes they were injecting in the scenario. So on the left-hand side, you see the bright spots that indicate the location of primordial black holes. They're very rare and they're isolated, so they follow the standard cold dark matter. However, if the abundance is large, or the unity on the right panel, you see that already at redshift 100, you have a very rich structure. And this does not happen if you don't have this shot noise. In lambda CDM at this kind of redshift, you still have not formed structures. So as a rule of thumb, what they concluded is that basically primordial black holes are mainly isolated and follow lambda CDM scenarios if this combination of redshifts times 10 to the minus 4 is larger than the abundance. And then you can describe structure formation using Preschechter description. This is what is done usually in the context of large-scale structure. So basically, your variance of density perturbation scales like Poisson, if the dominant contribution comes from primordial black holes, and you can write down the halo mass function, so the distribution of halos in terms of number of primordial black holes within them, and this matches the numerical simulations that they performed, and then you have to extrapolate the results beyond redshift 100, so beyond what they could test with their simulations. And there's one important point to be made is that small primordial black hole halos will evaporate in the sense that if the number of objects is small, through dynamical relaxation, you could have that black holes, once at a time, are thrown out of the system, and because they gain a velocity that is beyond the escape velocity. So there is a typical relaxation time beyond which these clusters evaporate. So your Halo mass function at one point, gets contribution from the collapse and the formation of visualized structure, but also gets depleted from the left-hand side from small masses because of this evaporation. So now we come to binary formation in these kind of environments.
Sorry, you may have said this, but since you showed redshift 1000, at photon decoupling, we know that the typical overdensities are order 10 to the minus 5. What is the reason why these primary black holes would show a similar fluctuation spectrum?
Those perturbations are at very large scales. So you probe it with CMB, so we're talking at very large scales. Here, we are talking at scales much smaller, so you wouldn't be sensitive to those perturbations. So that's the reason why. There are no constraints. I passed through a useful plot before on this. So this is the point. So CMB probes the amplitude of these perturbations around 0.1 inverse megaparsecs, say. If you want to form primordial black holes lighter than around 100 solar masses or below, in the range that I was showing is interesting, we are talking about scales that are beyond 10 to the 6 inverse megaparsecs, much smaller scales.
I understand, but if you want to use them finally as a part of dark matter, you would have to rely on an assumption that they show a similar fluctuation at late times.
At those large scales, you don't resolve those perturbations. They behave like cold dark matter, and you're not sensitive to the nature of. Could be also like it behaves as if it was a particle. It doesn't matter. Yeah.
A comment. It just simply move in the curvature fluctuations generated by inflation, just like particle dark matter, on the scales of the CMB.
Yeah. All right. So in these environments, you may form binaries through multiple mechanisms. So these can be classified in 3 ways. So either you form them in the early universe out of decoupling from the Hubble flow, and this is going to turn out to be the dominant contribution to the merger rate. And then you can have the formation of binaries later on in the universe after matter radiation equality, either through what is called by dynamical capture, so interaction of 2 bodies, or you can also have dynamical interaction of 3 bodies forming a binary. So this is what is also found to be the dominant contribution in astrophysical environments, like globular cluster. Dynamical formation of binaries proceeds through these 2 kind of formation. So let's describe how we compute the merger rate for these channels. So in the early universe, I said the initial condition is that you have primordial black holes distributed randomly. You should solve the trajectories of pairs of binaries, pairs of objects that on one end feel the Hubble evolution, and on the other end feel the interaction, the gravitational attraction. And so you can solve this equation in the sub-Hubble limit is Newtonian physics, and you compute the probability that these 2 objects decouple from the Hubble flow, and you can also compute the effect of the nearest black hole that will induce a torque on the binary and give it the initial angular momentum. So you can describe the distribution of semi-major axis and eccentricity that are the key parameter to understand how much time it takes for the binary then to merge through gravitational wave emission. Now, there are important effects that should be taken into account because the merger rate cannot be just estimated by only computing this initial condition. The point is that the rate is basically the integral of your distribution of objects on the number density, and you're integrating over the binary parameters, enforcing that the merger time scale is comparable to the age of the universe or fraction of it, depending on when you look at the merger rate. And a first important suppression of the rate comes from the fact that this initial binary is not isolated. So you should request that the initial configuration does not have a third object too close to it that will become bounded right away and will disrupt the binary. And this is done enforcing this exponential factor on the initial configurations that could end up being binaries later on. And also the angular momentum is in fact modified by the fact that you don't only have the closest object, but there are the distribution of objects in the universe and also matter perturbations of different scales as well that could affect the distribution of angular momentum of your binaries. So all this information should be taken into account, and in fact you can show that this slightly reduce the merger rate that you would otherwise compute. And then other effects can disrupt binaries later on after they're formed. And this was pointed out by Jedamsik and also Wan. And this is the fact that you have these binaries, they form at very high redshift. They could end up in clusters and in this small scale structure that you have in Primordial Black Hole cosmologies. And the point is that this binary would interact with other objects in these dense environments. And what happens is that following the Egge-Hills law, these are typically hard binaries compared to the environment, so their binding energies is large compared to the typical energy of surrounding object. So this interaction leads to a hardening of the binary, but they lose angular momentum. And in the end, what happens is that the merger time scale becomes much larger. Here you see on the x-axis the initial merger time scale, and on the y-axis the final one. So you see points after these numerical experiments lie above the axis. So those mergers will take so much time that you don't observe them now. So basically you lose them from the count, and the rate is suppressed. And the crucial point is that you need to compute the fraction of binaries that ends up in this dense environment that could disrupt them. It is sufficient that few of them, like a small fraction of them, always remain outside this dense environment, and there is a minimum merger rate that still remains there. So you're not suppressing all the binaries that you form in the universe. And this can be computed by computing the fraction of objects that falls in environments that are small enough that could lead to frequent interaction with the binary. And this suppression can be, here I'm showing results for stellar mass black hole, is at most around 10 to the minus 2, and becomes less important when you go to abundances which are much smaller than unity, up to the point in which you don't have a small cluster and the suppression is basically not present. Then you can also form binaries through Primordial Black Hole capture. Let me maybe proceed faster because I see I'm going slower than I thought. So the main point is that, as I said, gravitational interaction could lead to efficient emission of gravitational waves when two black holes pass close to each other, that you lose energy and the two objects becomes bounded. And a similar thing can happen when you have a third object passing through, and you can characterize these rays using results that were developed in the context of astrophysical environments. So to summarize, here you see the contribution from these three channels computed for a population of objects of around 30 solar masses. So this is the merger rate as a function of the abundance, FPBH. So you see for large values of the abundance, the dynamical channels taking place in the late time universe are very efficient and could be giving merger rates that are comparable to what is observed by LIGO Virgo. But the point is that the early universe channel is so efficient that it is by far dominant compared to the other. You see, in order to be complying with the bound by LIGO Virgo or staying below, you need an abundance of order 10 to minus 3. So this, in fact, is the way bounds at stellar mass in the stellar mass range were derived. So LIGO Virgo Cagra has observed many black holes mergers in the stellar mass range. So you can derive bounds with different assumptions. The most conservative is that you just require that the rate of mergers of your primordial black hole population in this range does not overcome what is observed, and you see that you find a bound that is giving you the abundance in the stellar mass range around 10 to the minus 3. And this is more stringent than other probes in this range. Then a totally another game would be to try to understand whether or not there are evidence of primordial black holes in these observations, but this is another game that I won't discuss today. I want to go to this ultra high frequency range. So we take these three ranges. We want to understand how they scale with mass. So you can do back of the envelope estimates. You see that in practice the early universe channel is the one that scales much faster, going to smaller masses compared to the others. So it remains as the dominant merger rate. So this is the formula that we will use. And also, let me just mention very briefly that in principle, accretion can speed up the merger, so it can harden the binary. And in the end, speeding up the merger will enhance the merger rate. You will have more binaries merging today. So in principle, can be used to enhance merger rate, but the point is that the accretion becomes very, very inefficient for light primordial black holes. Beyond the stellar mass, you don't expect to have any significant mass change due to baryonic accretion. So this is something we will neglect. Yeah.
In the late universe merger channels, two questions. First of all, was this done assuming a single primordial black hole mass or assuming a mass spectrum?
You can also integrate a wide spectrum.
But it doesn't change the results qualitatively.
It doesn't change the conclusion, yeah.
And the second question is, when you assume, when you're in the region of the parameter space where the primordial black holes are not all of the dark matter, what impact does the interaction with the remainder of the dark matter have? I could imagine that if there's particle dark matter in addition to the primordial black holes, you could have dynamical friction, for instance.
Yes, so there are two main effects. If there is a dominant component of dark matter which is not primordial black holes, first of all, you need to make an assumption that it clusters sufficiently at sufficiently small scales. So if it's an ultralight particle, it cannot stay so close to the individual black hole to have an impact. The hierarchy of scales is too large. If it clusters sufficiently, it can build a local halo around the black hole and around the binaries. So the first effect that it gives you a larger accretion rate. So the gravitational potential close to the binaries is larger, so the accretion rate is stronger, and you may have a different evolution due to accretion effects. And the second effect is, in fact, dynamical friction. This was studied by I believe Bertone and Kavanagh and collaborator. So there is an initial effect. The point is that the binary interact with the environment and usually gives energy to these particles surrounding the black hole. And so in the end, you end up with an halo around the binary. There is an initial effect on the semi-major axis and eccentricity, but this is usually small. This is what they concluded. But there are these kind of effects to be taken into account in these scenarios. But then, yeah. All right. So more or less, we arrived at the point we wanted to arrive. So we know how to compute the merger rate of primordial black holes. Now let's see in which plane we are playing. So this is a plot of the frequency of gravitational waves, and here I'm showing the strain. This is a collection of constraints coming from this nice living review, collecting the main efforts. It's probably already outdated, as people following the workshop already knows. But the point is that here you recognize at small frequencies the interferometers, LISA, LIGO, their sensitivity. And on the right-hand side, there are new ideas. You cannot necessarily use the same kind of physics to probe these high-frequency gravitational waves. And these experiments can be characterized in two broad classes. One is using what's called the inverse Gerstenstein effect. So it's basically the fact that your gravitational waves interact with the electromagnetic field in a similar way in which the axion couples to electromagnetism. And in fact, some of these constraints are really translating experiments searching for axions and taking their sensitivity on a gravitational wave passing by. And the other way that is proposed to search for these high-frequency gravitational waves is to search for the deformation of your device through the effect of the gravitational wave that's passed by, and you have to read out this deformation in some special way. So that there is a nice synergy between efforts searching for axions and also the one searching for high-frequency gravitational waves. And now we want to understand where in this plot signatures of primordial black hole dark matter in this nice window would end up. So there are different signatures. One is stochastic background produced from the mergers. So to compute this, you need to integrate the merger rate distribution in terms of masses and redshift, and also accounting for the emission of energy produced in each merger. And this is described as it is done in the LIGO band through the computation of the waveform and the energy release in the various phases of the spiral. And also you have to take into account the merger rate evolution of these binaries. And if you compute the energy density in this sector, assuming a given population of primordial black holes, here I'm reporting results assuming narrow populations spanning the mass range below 10 to the minus 6 stellar masses. You see that these spectra, in terms of the characteristic strain, remain below the line that identifies the delta N effective bound. This is a constraint from CMB on stochastic background, even though these are not necessarily bounded to be below that line because they are produced in the late-time universe, but still they give something at this level, and we are it will be quite challenging to reach this kind of level, at least so far. But there is another way. So this stochastic background is kind of the accumulation of different spirals throughout the universe evolution. But you can try to be more lucky and to search for individual mergers that may be closer to each to us and to our detector. The way one can quantify how lucky you need to be is given the rate of mergers, you can define the typical distance of a merger within, let's say, that would have a rate of 1 per year. So you integrate your merger rate, and you find the distance up to which you expect to have at least one event per year. Of course, there is a Poisson counting uncertainty on this, but this gives you the typical scale, the distance of a merger that you would have at least once per year. And you see that if you plot this distance going towards smaller masses, there is a large jump around 10 to the minus 6 stellar masses. because of the impact of the local dark matter overdensity in our galaxy. So at these distances, you see you are going below hundreds of kiloparsec. So you start seeing the local dark matter enhancement that is, of course, giving you a larger density of objects and potentially of binaries close by. But still, the typical scale is of course scaling with the mass, and for the 10 to the minus 11 or 12 solar masses in the open window, you see we are talking about an event per year in a kiloparsec volume, so a kiloparsec cube volume. And then, if you want to compare the signature of this individual merger, you can take the formula. This is standard results from the evolution of binaries through gravitational wave emission. And the crucial point is that these binaries have a typical evolution that dictates how much time they spend on a given frequency. Just because emission gravitational waves makes them lose energy, and their semi-major axis shrink, and the frequency becomes larger. So the gravitational wave emission dictates how fast the spiral goes and how the binary sweeps through the frequency range. And this is important because it can be the dominant factor when you compute your sensitivity of your experiment. So the integration time for your experiment is potentially dictated by this fact. And the point is that close to the ISCO frequency, the typical duration of the signal is the inverse of the ISCO frequency itself. So if we are looking at gigahertz peak frequencies, the time the binary spends at that frequency is so small. So it is possible that one is necessarily constrained to look at the earlier phases of the spiral when the frequency evolution is lower, and this allows for a longer integration times of your signal in your detector. So and here I'm coming to the final point that I want to make. Here you see these lines represent the signal written in terms of characteristic strain, which is the square root of number of cycles at a given frequency times the typical amplitudes. And here I'm normalizing the amplitude of the signal to this distance that will give you one event per year. And the point is, if you compare these signals to the sensitivity in the ultra-high frequency range, you will naively conclude that we are quite close to sensitivity. And it could be that you're very close to setting meaningful constraints on these scenarios. The point is that you see these colored squared or dots indicates epochs to mergers. So if you want, this tells you how much time is left for the binary to sweep through the remaining frequency range. And you see for the heavier masses plotted here, close to the kilohertz or megahertz frequency range, you see we are already talking about seconds or milliseconds. This becomes longer if you go to smaller masses, just because you are in an earlier phase of the spiral, but also the amplitude goes down. And the point is that many sensitivities are not necessarily taking into account that the time integration of the signal is so small. And what we tried is we take some of the designs for these experiments. We plotted the corresponding sensitivity in terms of just the gravitational wave amplitude, accounting for the integration time that is dictated by the intrinsic binary evolution.
Sorry, can you point me to where is the legend for the epochs to merger? I don't see the squares, and what do the squares and circles mean?
Just this line. This line would be gigayears to merger.
And,
it's basically related to.
No, I understand what it's related to. I just wanted to see the time, but now I see it.
Yeah, sorry, it's just indicated here. Yeah. And you see that when you consider this into account, things are much more complicated. And in particular, at higher frequencies, this picture is misleading. So there are a few orders of magnitude still to be gained, but at least in this megahertz frequency range, things may be more promising. So I think I'm running out of time. We can skip this part, but basically, I just want to conclude saying that, of course, primordial black holes are a very special dark matter candidate. We will be probing these scenarios with gravitational waves throughout a huge range of masses in different ways. So there is an interesting parameter space that could be probed by high-frequency gravitational waves. And of course, as you saw, it is a challenge to reach the sensitivity needed to set strong bounds on this scenario. But there is a nice synergy between this kind of high-frequency searches and axion experiments. So maybe it would be useful and fruitful to develop new ideas in this field, and potentially in the future get to the necessary sensitivity. So before concluding, just saying that there is the ongoing reviewing process of the Living Review. I'm helping with the section on late universe sources. So if you have a suggestion on ideas, get in touch. There was already a group of people that gathered during these days, on Mondays in particular, to discuss how to proceed, and just talk with me and get in touch. Thanks a lot.
Thanks a lot. Great talk. Do we have any more questions?
Very nice talk. Thank you.
Thank you.
Imagine in the far future, people will detect some stochastic background gravitational waves. How will you be sure that it's primordial black holes instead of something else?
That's a very good point. So far we only discussed about trying to reach the sensitivity. When you see something, of course, hopefully we'll be able to see something. The question is how you distinguish this with other sources. We know primordial black holes are a nice source there. There are other ideas. It will go like it is going with LIGO and PTA. So there are different features that you may use. The most obvious one is the spectral feature. So you need to be sure your spectrum of gravitational waves is indeed only possible in your model. There are no other scenarios that could mimic your scenario. So for the stochastic background from mergers, we know that the tail at low frequencies is dictated by the spiral phase. So it has a given frequency evolution at frequency to the 2/3. So there are features that may be used. But of course, as we have seen for PTAs and LIGO, it's going to be difficult. But yeah, maybe if we reach the sensitivity, we have already done most of the work. So yeah.
Yes, thank you for the very nice talk. It was really great. So I have two quick questions. Maybe you never mentioned transient phenomena. You discussed a lot about binary systems, but would you agree that binaries are hard to form, and more likely we are expected just transient phenomena like hyperbolic encounters from those objects?
So hyperbolic encounters is of course a possibility. There are large uncertainties on the rates, as far as I know, but I know that there's groups working on this. So it is something one should look at. Maybe the main argument potentially against saying that may be more stringent than looking for binaries is the fact that these are very fast bursts of gravitational waves. So the time duration again is probably close to the ISCO of analogous binaries. So the time integration of your the time in which you can observe these bursts is very limited. So maybe more challenging to do that, to search for these objects. In the LIGO band, for example, we know that searching for binaries is more giving you more stringent bounds. So, but still, I agree with you that kind of signature should be understood better. It is currently more uncertain. Yeah.
Can I ask you a second question quickly?
Okay.
Okay, thank you. I'm very surprised that when you take into account the time duration of the signal, it does not kill your sensitivity more than that. Because when you look at the whole range of masses which are accessible, for example, at the gigahertz, you go from 10 to the power minus 6 solar masses towards the lowest masses accessible, so 10 to the power minus 18 solar masses. And between on this range of masses, the time duration varies on many orders of magnitude. So here, if I understand correctly, it impacts your sensitivities in like what, 4 orders of magnitude, something like that?
So if you want here,
At
sorry, just a second. Here it is. So in this plot, basically what we are doing is the following. There is a given experiment, so we compute the sensitivity you would have to a binary of these masses shown, and the time of observation is dictated by the time it takes for the binary to sweep through the bandwidth.
Yeah, exactly.
Yeah. So and the 4 lines correspond to the 4 masses we observe. So there is basically a trade-off. So with smaller masses, the time it takes for the binary to be at that frequency is longer. So the sensitivity is enhanced, but also your amplitude goes down.
Yeah.
And so there is a trade-off. It seems that it's winning going to larger masses.
Okay,
Yeah.
I'm asking that because with Ron we performed similar analysis, and in the case of resonant cavities at the gigahertz, we observed that the sensitivities drops to much greater values than that, like 10 to the power minus 14 on the
Okay,
strain.
maybe we should look at this later.
Okay,
Yeah,
thank
I'll
you.
be happy to discuss, but yeah.
Yeah, thank you.
Joachim?
You showed on yours, you argued that the most efficient binary formation channel is the early universe channel, and you had a plot on that on your slide 31 where you did that for a 30 solar mass black hole.
Yes.
I was wondering how this conclusion scales with the primordial black hole mass. In particular, my question is if the supermassive black holes that we see at the centers of galaxies, if those were primordial in origin, would we then not have a final parsec problem? Because binary formation would be much more efficient.
So the answer to the first question is this one. So you take the rates, you see how each contribution scales with the mass, and what you end up discovering is that the early universe binaries goes much steeper with the inverse of the mass. So going towards smaller masses, indeed, this is your expectation. If you go to large masses, if you want to connect maybe primordial black hole to supermassive black hole merger, that's very difficult because to have rates that are kind of comparable to what PTA is expected to be comparable to, you need large abundances. There are papers on this. I think Kai Schmitz that was here had a paper on this, but there are different groups that work on this. And the typical values of the abundance is over there 10% or so. But at such large masses, there are huge bounds. So it's very difficult to do this. Regarding the final parsec problem, indeed, if you form the binary with dynamical capture, you are directly in the gravitational wave dominated regime. So the binary evolution already proceeds through gravitational wave emission, so you wouldn't have the final parsec problem. But the point is that scenario, for other reasons, is very well constrained. Yeah.
Thank you, Gabriele. That was a beautiful talk. Now, there's an issue with non-Gaussianities. Of course, you didn't treat that fully, but it's clear this is more a comment than a question. If we know that there are large non-Gaussianities, of course, we don't measure that at the CMB level, but those are very large scales. We can think of very small scales where these objects form, would induce whatever the mechanism that produces them, maybe quantum diffusion, some other sources. You would have large non-Gaussianities, which would first make them much more probable to perform, and second, they would be clustered in a very sophisticated way. I agree, it's not just simply Prashakter, but there is a way to compute the clustering. And this might change completely your merger rates.
Yeah, this is something I didn't touch upon. I only had one slide on this. I agree with you that non-Gaussianities are important when you compute primordial black hole abundance, but non-Gaussianities needed to cluster primordial black holes are very specific and difficult to have, as far as I know. The point is, One thing is having non-Gaussianities at the scale of the small-scale perturbations that are produced in the collapse. And one other thing is having non-Gaussianity as the scale of the typical distance of your primordial black hole. So if you want to cluster primordial black holes, it doesn't matter the small scales. The only thing that matters is the typical distance. So there is a hierarchy between the scale where you have the enhancement of perturbations to produce a collapse and the scale at which you need non-Gaussianity to cluster them. And typical scenarios, as far as I know, are not generically producing this kind of non-Gaussianity. So it must be local and potentially scale invariant for many decades. So I'm not saying it's not possible or it's not generic.
Quantum diffusion is precisely what you get.
For quantum diffusion, I have an argument against this because ultra-slow lasts for 3 folds, so you don't have enough decades to reach the distance case. But okay, maybe we can discuss this more in details. Okay.
Okay, I think that's maybe a good time to go for coffee and continue the discussion over coffee. For the workshop participants, let's come back in half an hour, right? So at 20 to 4 back here.